Okay. So the topic that we'll start with today will be on natural vibrations, and basically all objects have their own characteristic sounds. Okay. Say for example, this whiteboard has a kind of characteristic sound. So if you tap on it, there is a very distinct sound that comes off it. You can say that it's distinct in the sense that most whiteboards of this kind of size and this kind of material, and probably some other materials like wood also, would produce a similar sound when it is struck. Since it's producing a sound, it's obvious that something in the material is vibrating. In this case, the entire surface. So you tap this, there is a vibration that happens in the surface. That vibration pushes the air molecules and the sound propagates towards the mic. And then whatever, it gets translated into electrical signals, and then it comes to you and you hear it. If you were all here in the classroom, you would hear it naturally. This water bottle has a distinct sound, right? Because it's made up of a different kind of a material. In this case, it's metal, right? It has its own distinct frequency, right? Similarly, if you take a surface, let's say like this, it's a bound textbook, and it has its own distinct sound. Okay. Now, the point being that all objects, when they are struck, seems to have some kind of a natural frequency with which they vibrate, and therefore a specific kind of sound that it produces. And of course, you will be able to then, if you hear it enough number of times and also see where the source is, you will be able to create in your own mind a kind of a mental library for the sounds. Obviously, the same thing also happens with people, right? So there is a distinct quality to people's voices, which when you hear, gives you a picture of what this person is. So like, for example, right now you're not able to see me, right? But you have heard me before, you know who I am. And if I speak, it kind of evokes a natural picture of the person in your mind. I don't know if that's a good thing or not a good thing, but that's what happens. So you can imagine that I am the one who is speaking. You don't need to, it's not something that is kind of removed from the person or the object from which the sound comes. So natural vibrations, therefore, are distinct vibrations, distinct sound waves that are produced by some objects. One moment. I'm just letting Varsha in. Okay. And that distinct quality is something that has got to do with the material of the object and the properties of that material. Okay. So if you now look at the textbook, so that's just a kind of an intuitive understanding of what I mean by natural vibration. So if you look at the textbook now, and we are on page 155. We'll just do a little bit of like figuring out the textbook. It says, the periodic vibrations of a body in the absence of any external force on it are called natural or free vibrations. External force in the sense that, imagine a guitar string. So many of you play these instruments, either a guitar or a sitar, and a lot of you would have also played around with it even if you don't play it. So you all must know that the guitar string or the sitar string produces a specific, it's meant to produce a specific note, and that note can change depending upon certain external conditions. Like say for example, if you are not going to be playing your sitar for a long time, or you are traveling with the sitar or guitar to some other place, it's a good idea to loosen the strings a little bit while traveling. Am I right? I have heard musicians say this. I don't know if you people
Yes.
practice it, but does it make sense to do that? Why?
Because
Somebody
if
said
it's
yes.
tight, then it could get stretched because of temperature and break.
Yeah, exactly, right. So if you keep it too tight, and let's say that you happen to go to some place which is cooler, okay, maybe it's going to be stored in a place where it's going to get very cold. Like say for example, the hold in an aeroplane, right? There it gets very cold because that is not climate controlled. So then what can happen is the string can shrink. The shrinkage in the string can actually cause the neck of the instrument to snap, or the string will break. Sorry, the neck of the equipment obviously will not break. The string will break.
Sir,
Yeah,
is it related to the tracks of the railways, the gaps and all the stuff because of the temperature?
linear expansion. Because of the coefficient
Yeah,
of linear expansion, there could be issues.
yeah,
Now, naturally, when you go to wherever it is that you are going to perform or use the instrument again, then what you need to do is you would have seen this. Anybody who has attended any kind of a live performance, including in our school, right? The people who play the instruments, the musicians, they spend a bit of time depending upon whether if they are seasoned musicians, they can do it quickly. Like you see Telang sir, tuning his tabla in the morning before assembly. Um, and if you yourself had tried it, it's very hard. I have tried it to do it by ear, and it's very hard to do it if you are not trained. So if you do it a number of times, then you get it right. But it takes a little bit of a time getting the tune right. Okay, so that's I think the kind of idea that they are talking about over here. That is the periodic vibrations of a body in the absence of any external force applied on it. This is called as the natural vibration. Just one moment. Okay, so that's I think, because if the external forces are applied on it, then the natural frequency of the object can be changed. All right, so I think that's the point about external forces. Any questions at this point of time? Any questions about natural or free vibrations?
So to produce a vibration, don't you need an external force?
Exactly. So that is the confusion in it. So no matter what happens to be the natural frequency of, let's say, the skin that is drawn on the tabla, you won't know what it is unless you strike it. So we are not talking about external forces that cause the vibration to happen. Momentarily you have to hit it, right? But once you have done that, it vibrates at a set frequency, right? And you can also see, so basically, shall we stick with the tabla or shall we go to the tabla is a little more interesting that way. Okay, we'll go to the tabla. So you see, when you strike the dhakka. So if you watch Telang sir carefully when he's playing the tabla, or anybody playing the tabla for that matter, when they hit the dhakka, they also press down with their wrist, this part of it, the mount of Venus as it's called when they are looking at your, what do you call this, palmistry. They press and then they push. Okay, so they strike it and then they press and push. And what does that do? Have you noticed this? You can also do the same thing with the guitar string. You pluck the guitar string, you keep it on one particular fret, and after you pluck, you move it. They do it in a veena sitar a lot more than they do it on a guitar. But what does that do?
Changes the frequency.
It changes the
So
frequency.
the pitch is bend, like pitch bender basically.
Yeah, so it changes the pitch. So when you strike the dhaka, sticking with the tabla example, there is a certain frequency with which it vibrates, which is its natural frequency. Okay. Now, when you press on the dagga, you increase the tension on the skin. Okay. So that means the natural frequency will then change. Why? Because you are applying an external force. The first strike that you did, that doesn't matter. That just causes it to vibrate at its natural frequency. But then when he presses with his wrist and pushes, then he changes the frequency of it. So that should be constituted as an external force. So you can't say that, well, there is a guitar string and it plays whatever, G sharp or A or whatever. Okay. But then when you press on the fret and you move it around, then you can change its frequency. So you say, what is the natural frequency of the string? So then you say the natural frequency of the string is the frequency with which it will vibrate if you pluck it and then allow it to vibrate freely. If you apply force on it by either stretching it more or decreasing its length or increasing its length, then naturally the basic property of that material has changed, so its natural frequency will also change. Is this clear? Any questions?
Yeah.
Yes. So Saumitri and Kian, I agree with your comments. Yep. Okay. So in case you haven't looked at the comments, the last two comments from Kian and Saumitri kind of sum up whatever we are talking about. Okay, so then now let's get back to the textbook and see if we agree with the points that are written over there. First is that this is giving examples of natural or free vibrations. It's a good idea to know these things because these are possible questions. If the bob of a simple pendulum is displaced, blah, 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 so then it starts vibrating at a certain frequency. So theoretically speaking, this is what they call as free vibrations. See, one question that routinely is asked with regard to this is that the point being that the questions that they generally ask, which can be a little cryptic if you don't understand like what is it that they are driving at. So they'll ask you something like, what is natural vibration? Okay, what is the natural frequency of an object? There are two parts to it. First thing is that the frequency that an object produces when there are no external forces acting on it. So do you get the 2 points? The 2 points is the frequency at which an object naturally vibrates when there are no external forces. So both these points must be mentioned. Okay, and sometimes there is a variation of this question which can throw you off if you are not prepared for it, which is that question they'll ask is, under what conditions does an object undergo free vibrations or natural vibrations? Okay, so you start thinking, what are the conditions under which natural vibrations will occur? So what would be your answer? Did you get the question? The question is, under what conditions will an object vibrate with its natural frequency, or under what conditions will an object have natural vibrations? Ishan says it will have to be in vacuum. Yeah, in vacuum also, technically speaking, yes, an object can undergo natural vibrations, free vibrations, but since we are talking about sound, it doesn't make sense because in vacuum there's no medium to propagate it. People do write that answer, and I'm not sure whether that is an acceptable answer or not. The correct answer would be where there is no eternal forces or external forces. Arav, you wrote eternal forces. Okay, so you have to write that where there are no external forces, an object which is vibrating when no external forces act on it, that object undergoes natural or free vibrations. And of course, if you think about it carefully, this is not possible at all. It's another one of those ideal situations which are required for us to discuss what actually happens when we say that there are no external forces. But of course there are external forces, because we know that simply because anything that has been caused to vibrate will not vibrate endlessly. It does come to a stop eventually, right? And it comes to a stop because there are external forces involved. So those external forces cause what is known as damping. Okay, so there are in reality no objects that we can think of which will have completely natural or free vibrations. A huge truck is just rolling by with bricks in it. So there's a little bit of noise in the background. Okay. The only place where there aren't, but what, so yeah, the question is, it's not a place, under what conditions? And the other thing is that what is this object that is vibrating in vacuum that does not have external forces acting on it? Can you give an example? See, unless we go to the subatomic world, we can't talk in terms of natural vibrations of object which will continue forever with no damping forces, or so little damping forces that we can more or less consider it to be absent. Okay, so if you say yes, there are objects that can vibrate in vacuum, then you don't have even air particles to cause any friction. But then what is this object that is vibrating? Is it a pendulum? Then what about the string? The string has to be hung from some object, right? And what about the tiny amount of friction that occurs between the string and whatever it is that is holding it? Right? So in that case, you will have to specify what is it that is vibrating, which does not have any significant damping effect. So to move on from there, a load suspended from a spring when stretched and released also undergoes natural vibration. So yeah, so that can be one another kind of an example. So if you have, right, something like that, and if you were to stretch this, right, and then release it, so what will happen is the restoring force in the spring will cause it to move in the upward direction. So then it will move upward until it gets compressed completely, and then gravity will take over. So then there will be this kind of an oscillating motion. Of course, there is some damping forces that are involved over there, but this can go on for quite some time. Then a tuning fork is stuck against a hard rubber pad. Again, we have seen that example. When an air column in a flute is made to vibrate, it vibrates with its natural frequency. Then when in a string instrument like sitar, violin, etc., when the string is plucked, it vibrates at its natural frequency. So I guess pretty much anything that you are talking about in terms of objects producing sounds, you can say that if there are no external forces that are applied on this object, then that object will continue to exhibit its natural frequency for as long as the forces are not applied. Striking the keys of a piano, and the last one, string of a given length stretched between its ends under a given tension can be made to vibrate. Okay, yeah, that's fine. It's more of the same thing. So any questions about whatever it is that we have read so far? If there isn't, then we can move on to the next section. Somebody keep track of the time and just let me know, as usual, it's coming close to the end of the class. This is supposed to go until 10:55, right? So let me know at 10:50. That's in about another 12 minutes from now. So let us now try to quantify natural vibrations a little more. Okay, since there are no real objects that can actually, macroscopic objects that can actually have these kinds of natural vibrations, how do we quantify it? Okay, so we again go back to the graphical representation where we are showing displacement in the y-axis and the distance that an object moves, or rather we are doing time now, okay, time in the x-axis. Now an object which is undergoing natural vibration, or the particles of the medium that are undergoing natural vibrations, they are going to have a fixed amplitude. Okay, so we'll measure some height. And we fix the amplitude to that particular height, both about its mean positions. So now if you see a wave, a sound wave that is being produced, which has natural vibrations, then it's going to kind of look like this. Okay, so this may be something that you will be asked to either sketch. Rarely happens that they ask you to sketch, or they will ask you to interpret. Okay, so a question can be, show how can you represent an object which is undergoing natural free vibrations graphically? Represent graphically an object which is undergoing natural free vibrations. So then you show your graph like this. Okay, where the amplitude of the object does not, the amplitude of the displacement of particles of the medium do not vary. Okay, you don't have to be too worried about drawing accurate diagrams, but it's a sketch, so you kind of indicate that in time the displacement about its mean position does not reduce. Is that clear now? What kind of questions can be asked? They can give you a sketch, ask you to interpret whether it is undergoing natural vibrations or is it damped vibrations, or they could give you the situation and ask you to draw the graph. In which case you make a sketch like this. You don't have to do an accurate version, but you try to show as clearly as possible the different parameters. So regarding graphs, let me just repeat once more. They typically give 2 to 3 marks for graphs, so you can immediately see that the first couple of marks is just for representing it correctly. Say for example, what is on the y-axis, so you show the y-axis, mark the y-axis and show what is being marked out on the y-axis. So displacement in this case, draw the x-axis, show which is the x-axis and show what is represent on the x-axis. That itself can get you half the number of marks that are being awarded. And then the rest is of course to show whatever it is that you are attempting to answer. Okay, so that will constitute the rest of the marks. Make sure that you make graphs large enough so that if you break the sheet that you are using into a quadrant, into 4 parts, your graph at least covers 2 parts. Okay, it can cover 2 parts like this or like this. I suggest this is better. Okay, so don't draw a tiny little graph like that over there. That doesn't work very well. It's a good idea to display things clearly as far as possible. You get it? So this is not on and this is fine. Okay, Saumitri got kicked out for some reason. Okay, so now moving on. So if this is the graph for an idealized situation where natural vibrations are taking place, there are no external forces acting on it. What will happen if there are external forces? That's easy to see. If there are external forces, then okay, so let me put it as a question. If there are external forces that are present when an object is oscillating, vibrating, then which quantity will reduce? Okay, so in the presence of external forces, will the wavelength, frequency, velocity or amplitude, which of it will reduce? Okay, careful now, I'm trying to trick you. What can you say in terms of what we have looked at so far? What can you say definitely will change? Vaishnavi, you'll have to check your mic setting because I think everybody else are able to hear well. Yeah, so my question is, in case there are external forces that are applied to an object that is producing a sound, a natural vibration or a natural frequency, which of these quantities will change? Or which are we certain will change? Yeah, as many people are answering, yes, certainly the amplitude will change. Okay, we can be sure that the amplitude will change. Of course, it is also possible that the frequency will change. Say, for example, in case you increase the tension in the string, you pluck a string and you increase the tension, then the frequency will also change. Okay, I'm just wondering if there are any examples in which uh, only the amplitude will change, but the frequency and the wavelength will not change. So if you pluck a guitar string and you just allow it to, uh, just play by itself, right? Then the frequency and the wavelength will not change, right? But over time, what will happen is that the amplitude will keep reducing until all the vibrations have died out. Is that clear what I'm saying?
Yes, sir.
Yeah. So the amplitude is the one about which we are certain that there will be a change in the presence of an external force. An external force can of course also change the frequency and the wavelength. But if you talk about an object which has been struck, like I'm going back to my pink water bottle. It's my water bottle. I stole it from Kabir. Okay, I admit it. If I strike it, it produces its natural vibration, but it doesn't go on for a long time. It dies out pretty quickly. I'll kind of keep it close so you can hear it. So what is happening in this case is the frequency and the wavelength are not changing, but the amplitude is changing, and it's changing very quickly in this case. So if you have to represent that, the change in the amplitude, right, then I can do it using the same graph. I hope you people are taking down notes of these things. Practice makes perfect, you see. Then the sound is now going to get reduced as time goes. Okay, so the amplitude is going to be continuously reduced as time goes. So I know that it's going to reduce. I've looked at the graph in the book. So what I can do is I can kind of make a guideline for me like that. Okay, so try to keep it almost equal on both sides, and then show the graph like this. Okay, now that graph then represents a wave, a sound wave that has some external force acting on it and therefore is damping it. So there is a damping force present. Therefore, the amplitude reduces as time goes ahead. Okay, so these are two ways in which you can graphically represent what is going to happen when there are no external forces present and external forces present. So I hope that makes it clear what natural vibrations are and damped vibrations are. What remains to be seen is forced vibrations, and we can pick that up in the next class. So coming back to the textbook very briefly, I noticed that it's kind of like a minute to 10:50. So we should start winding down. is that the examples, what are the examples of an object having free vibrations? Have a look at that, mark that section. You need to know one or two examples that you can repeat, and it looks like almost anything that you can think of in terms of vibrating objects that produce sound, you can write. So you can write a piano, you can write guitar, you can write sitar, you can write tabla, whatever it is. Okay, this the easiest one to remember. Okay, I won't say the easiest one to remember, but whatever is easy for you to remember, put that in your noodle. Then we come to the damped vibration section. What is, sorry, the graphical representation of an object undergoing natural vibrations without external force, what it looks like, and damped vibrations when the amplitude of the vibration reduces in time, and then how it is represented graphically. Then examples of damped vibration, oh God, when a slim branch of a tree is pulled and then released, it makes damped vibrations. People like that example, they write it a lot. They ask this question once every couple of years. A tuning fork, when stroked on a rubber pad, executes damped vibrations. So some intellectual dishonesty over here. They say that they give the same examples for natural vibrations and damped vibrations also. Okay, well, that's how it is. Spring is mentioned,
So
film is mentioned. Yeah,
I have a question.
please.
I don't really see a difference between natural and damped then. I mean,
Natural vibration is an idealized situation. Imagine a flat plane which is endlessly long, infinitely length, infinitely
so it,
long, and zero friction. It just helps us to think in terms of what will happen if there are no frictional forces and an object is moving. And that gave rise to the concept of inertia, right? So similarly, this is an idealized situation, an object undergoing vibration with no external forces acting on it. So what will happen? Well, its frequency will not change, its amplitude will not change, its volume will not change, etc., etc., etc. So then we can examine what happens when the external force is present, which is the reality of things, which is how things actually are. Okay?
so generally it's damped vibrations, right? Like
Yes,
around,
we generally observe damped vibrations all the time.
and natural vibration is like only in vacuum.
No, no, no. Even in vacuum, that's what I was discussing with Ishan. So Ishan was saying, technically speaking, that can happen only in vacuum. But I'm saying, what is vibrating in vacuum that is having natural friction? Because you have to hang an object, right? If you have a pendulum which is oscillating in vacuum, very good. You have removed air friction. You have removed air drag. But the pendulum string is stuck to something and it is moving over there. So that chafing is also a little bit of friction, which will eventually kill the vibration. So there is no such thing, except if you go into the subatomic world, right, where there are objects which are undergoing more or less natural oscillations with zero external forces. You get what I'm trying to say?
Kind of.
Kind of, okay. So then the last thing, so think about it. So the last thing is that differences between natural vibrations and damped vibrations. So
Sir,
look at the examples, look at the differences between the two. 1 or 2 points you ought to commit to memory, so that if they ask a question like that, give 2 points of difference between natural and damped vibrations. You can draw a tabular column and show the differences. So that's as far as what is given in the textbook is concerned. So we are done with this section. When we come back for the next class, we will look at what is forced vibrations. So do come having prepared yourself a little bit. Those who want to leave can leave. If somebody has any questions, I can stick around for another couple of minutes.
sir, are there any examples of natural vibrations in the subatomic world, or are you assuming that there might be?
You see, the path of an electron around the nucleus, right? That could be looked at as something that has periodic motion. It has a periodicity, right? So the periodicity then shows us that there is some kind of an oscillation. So if there is something assuming going round and round, then there's a certain frequency with which it is doing that. So there is no reduction in the velocity at any point of time. So within the subatomic world, simply because forces like friction just don't exist at that level, at least looking at it classically in terms of classical mechanics. So then you can say that under those particular set of conditions, we can say that there is natural vibration taking place, in the sense that there are no external forces that are damping it. That is my assumption. Of course, I'm not sure that it exactly is so, but that is my assumption. That's what I mean by saying in the subatomic world, because
Yeah, okay.
concepts of classical mechanics don't quite work over there. So it's not quite kosher to mention that as an example, but I'm doing it. Okay, so we'll stop here now. See you guys in the next class.